All right, everybody, welcome to COVID Calculus number 5. It's been lasting too long. So we got, in this case, we're actually looking at a pig trough. So a pig trough that looks something like this. If you're at all familiar with it, if you grew up in the country like I did, it's what you use to feed pigs and other livestock. So you have a trough that's 10 feet long. So this length here is 10 feet. It goes back that way. And this is an isosceles triangle. The isosceles triangle has a 2-foot base, right, which is the top part here. So it's flipped upside down. And then the height, which is this center line here, is going to be 2.5 feet. Okay, and there's a point there. Okay, this is a tricky one. So what it gives you is that a farmer is pouring in swill, which is the food, at 1 cubic foot per minute. So what I'm going to call that is V plus prime, right? Equals 1 foot cubed per minute. Okay, so that's the speed at which the volume is changing it's increasing. Right when the farmer reaches the brim, he releases his 3 pigs, who then come violently sucking down swill. Each pig eats 1/2 cubic foot per minute. So I'm going to call this V negative. There are 3 pigs, each eating 1/2 foot cubed per minute. And in addition to that, because they're eating so violently, they're splashing out an additional half square foot. Okay, and keeping in mind that this whole section here, this is the negative. Okay, so I'm just going to put a negative on the outside here. Okay, so it's letting you know that this is the amount that's changing. The question that's being asked is that when the swill falls to 1 foot 8 inches, so 1 foot 8 inches will be the height. Okay, so let's say when it falls to, I'm just going to draw it down here, let's say 1 foot 8 inches, somewhere around there, okay? And this equals 1 foot 8 inches is, what is that, 1 and, is it 2/3? So we'll call it 167 feet. Hopefully I did my math right there. And it's asking how fast the swill level is falling. So it's asking for the derivative of h. Okay, this is our question, and this actually gets kind of intriguing. Okay, so let's start here. So that we have a volume that it's increasing by and a volume that it's decreasing by, which means that there's going to be one single volume that's either increasing or decreasing. We just have to add these together. So in order to do that, I'm going to take 3 and multiply it by 1/2. And you get 1.5, right, cubic feet per minute, plus 1/2. Well, that equals 2 feet per minute, right? Negative 2 feet per minute, cubed per minute. Well, that's the negative side of it. And then we're also filling it by 1 foot per minute. So the actual derivative, or the change that's in volume, is just going to be -2 plus 1 is -1 foot cubed per minute, right? Okay, so awesome. Now this is where it gets kind of complicated. So it's not asking for the change in volume, it's asking for the change in height over this period of time. And in order to do that, we need to actually consider, okay, well, what is the volume actually calculated to create? You know, what are we using in the volume? Well, we have a length here, we have a height here, and we have a base here. Well, the volume of this shape here is going to be 1/2. Well, actually, let's back that up. It's going to be basically the area of this triangle multiplied by the length, right? So you basically have a whole bunch of these triangles infinitely long or infinitely small all the way to the end. And you're calculating the areas of those as they go through. So you could say it's the area of the triangle times the length, right? If you continue to simplify that or expand that, you get 1/2 base times height. That's the area of a triangle times the length. Okay, so we're kind of digging our hole here, and we're going to dig back out eventually. But we have this volume here, and it's asking us at this point, how fast is this changing? This takes some forethought here, okay? So first we have to consider what things are changing as we go through this. Well, the volume is changing, right? The base is changing. As the height drops, the base gets smaller, right? So the base is changing, and the height is changing. That's 3 different things that are changing. The length, however, is not changing. So that's kind of nice. That simplifies things out. Well, let's kind of figure out what we can do with this. So one thing we're going to need to do is take a derivative. Well, we have 3 variables that we're taking a derivative of, one of which we know the answer to. That's the derivative of that is -1. So that we can kind of rule out. We don't have to worry about that. But we have 2 variables here. So what I need to think of is, how can I simplify this into one? How can I reference one of these to the other? And really what you have to think about is, well, we're being asked to solve for h. So let's keep h. So let's try to figure out how we can do this. So moving back over here, we have this big triangle here, and we have this little triangle here. Well, just because it shrank, it doesn't mean they're not similar. They're actually very, very similar triangles. They have the same angles there. They have the same angles here, and they have proportional sides. So what you can say is base, height. We're trying to find a ratio for these, right? Well, the base of this upper triangle, the base of this, let's say the lower triangle, or of any triangle as we go through this, ideally, that's why we're using this variable base, is going to be proportional to the base of this top one. And the height is going to be proportional to the height. Okay, so we're saying base is to 2, is height is to 2.5. What we've done is basically created a ratio to any triangle that fits within this related to the original. Now we can actually solve for base, right? So we get multiply by 2.5. Excuse me. Multiply 2 over, since we want to solve for base. So we're going to have base equals 2h over 2.5. Well, simplifying this, think of it as like 20 over 25. That's 4 over 5, right? So we're going to get, I hope that made sense to you what I did there. 4 over 5. All I did was simplify these out. Basically, you're dividing both by 0.5. There's 4.5s in 2, and there's 5.5s in 2.5. So you get 4, 5. Then I'm going to put it in decimal form just to make it easy. So 4 divided by 5 is 0.08. Okay? So we found out that base is the same thing as 0.08. So we've solved to substitute this base here. So let's go ahead and do this. We have v equals 1/2, plug this in, 0.8 h times h, right? There's the h, times L. Okay? And I use that funny L. I think that's by habit there. You can use a normal L if you prefer. Okay, so let's simplify this out. So let me draw a line here just to separate and give us some room. We have v equals, well, 1/2 of 0.08 is 0.4 h squared, h times h, right, times L. Well, L is a constant. L is right here. So I go ahead and plug that in, and we get v equals 0.4 h squared times 10. 10 times 0.4 is just 4. So we get v equals 4h squared. There is our volume formula here. Great. Well, let's find the derivative. And this is an interesting derivative. Normally, what you try to gain a derivative of is something like this. And this is a little bit of a tangent, so I'm going to draw it off to the side, okay? So normally, you have y equals, let's say, 6x squared. And you're trying to find y prime, right? A lot of times we'll write as y prime. And And that would be bring down the 2, you get 12x, right? There's your derivative. Another way to write it, though, is dy dx equals 12x. What this is saying is the change in y over the change in x equals 12x, right? That's rise over run. You know, that's the slope. You've found the slope of this. What that also means is for every small change in x, y reacts with a small change. Okay? That's because that's what you're interested in. It's kind of abbreviated like this. Well, what this also is you kind of think of it like this. Well, let's multiply both sides by dx, and you get dy, which is the change in y, is 12 times x times this change in x, right? So now what this is saying is the change in y is relative to x, right? Times this change in x. That's telling, because it's telling in the sense that in our scenario here, we're not worried about the left side with respect to the right side. There's a third piece going in there, and we know that because of this. I'm going to do it the wrong way first. So if I want to find the derivative of this, I would say, okay, give me dv, and I'm going to take the derivative of the right side, right? The derivative of the left side really is just 1 times dv, right? You can think of it as like that. So it's just kind of, we could write it like that if you wanted to. Let me go ahead and take that out there just to not confuse. So then I take the derivative of this, you get 8h, right? And this is going to be dh. Well, just as before, I could move this h over, and what I have is telling me the derivative of v with respect to the derivative of y equals 8h. Okay, that's interesting, but if you think of it like this, you're saying that the volume is feet cubed, right? So the change in feet cubed over the change in feet, which is the height, equals 8h. Doesn't really make sense. You know, it doesn't. Yes, they change together. You know, there's a relationship there. But what we were asked is how fast is the height falling? That means it's going to be in feet per minute or per second or per unit time. Okay, so instead of that, let's go ahead and cross that out. That's not what we want. We need to bring in this kind of third variable, if you will. So really what we're doing is this. We're saying, what is the change in volume with respect to a small change in time? As time progresses, some increment, how much does the volume change? Okay? And that, there's also a relationship in how the height changes per time. So what you do then is solve for the derivative of the right side, which is going to be 8h, just as before. But now we have dh. So the change in height given a small change in time. Now, this gets a little interesting because we know this. We didn't know the previous one, right? We solved specifically for the previous one. It was 8h. But that didn't really give us what we wanted. We wanted to know that. So we plug in our original change in volume per given time, which is right here. So we're going to take that. We're going to say -1 feet cubed per minute equals 8h dh over dt. This, again, is what we want. So what I'm going to do is take this 8h and move it over. So now I get -1 over 8h equals dh dt. Okay, that's wonderful. I've actually created a formula now that tells me at any given point what that unit change will be. But I actually have that point, so we can actually solve for that. That point, this is the height, right? Right here. It gives me that. It told me 1 foot 8 inches, right? And I think I 1.66 should be 1.67 should be roughly accurate. So what I can do now is say -1 over 8 times 1.67. And if I pull up my calculator real quick, we just multiply that out. 8 times 1 0.67. So now we get our answer being negative 1 over 13.36 is the change in height per given time at 1.67 feet height. All right. So this one was kind of tricky, and it's really, I think, kind of a core concept to kind of these problems. When you're asked a certain question of a unit change, there is a unit attached, and that unit attached is very telling into what you're actually looking for. If you just automatically find the derivative of the left and right side, you're finding a relationship, but it may not be useful. It may be a kind of pointless relationship. Kind of creates a unnecessary data or not at least of interest data. So what you need to pay attention to is what is the question that it's actually asking, and because of that, you're actually able to kind of figure out which direction you need to take it. And additionally, this pattern of finding similar triangles or finding substitution methods for certain variables so you can rule out them from the formula of interest is extremely useful, and you'll find that in a lot of different types of problems. But anyway, I hope that was of use.